Hi everyone, it is time to talk about the Wittig reaction. Remember, we are doing carbon nucleophiles attacking carbonyls, specifically aldehydes, ketones. And so the Wittig reaction is a name reaction that has its own name because it is special, but it does have kind of an interesting mechanism. So we're going to break it down into two major steps. And before I do that, I might just call attention to the fact that what's really exciting about this is a CC bond, because it's a carbon nucleophile forming reaction. Big deal, okay? So it's an important reaction once again. So I know we just learned the Grignard organometallics. Well, of course, that was a carbon nucleophile. If we're still doing carbon nucleophiles, we're going to hear about CC bond forming. All right, so what happens in the Wittig reaction is you get your Wittig reagent, your aldehyde or ketone, and you end up with an alkene at the end. So that looks different than anything we've done so far in this chapter. Two major steps that break down the mechanism. First, we have to make our reagent. Make my pen a little thicker. That's too thick. Okay. Formation of the reagent, the Wittig reagent, which is called the phosphonium ylide. Sometimes you'll hear it described as the Wittig reagent or the phosphonium ylide. Those are interchangeable. And yes, I'm saying Wittig with the V for the W because George Wittig was German and won the Nobel Prize in 1979, if I'm remembering correctly, for this work. So it was a very significant contribution. After step one, the ylide has formed. The ylide, that's a good word, ylide, attacks the carbonyl. So you may be new to this word, ylide. It is a substance in which two atoms that have complete octets are connected to each other, but they have opposite formal charges. That's called an ylide. I always thought that would be a good name for a cat. If I ever get to name any more of my cats. My kids usually name cats now, the pets of any sort. I think yllide's a good one, because they kind of have that two sides to them. So they're really nice one moment, then they turn. But I think that's endearing. Anyway, ylide. Here's an example of one right here. Full octet on carbon, but it's got an anion. Full octet on phosphorus, but it's got a positive charge. It doesn't have to be written like that. In fact, many times, because we don't like formal charges, we've just grown to see them as something very unstable, we will write the resonance structure, because we could just do this. Lone pair gets accepted by phosphorus to share with carbon. And look at these 3 phenols on phosphorus. Quite a designer molecule there. But that's the resonance structure, and that may also show up as your reagent because resonance structures are equivalent. So you may see the ylide, actually the Wittig reagent, represented as this form or this form. You want to recognize both, okay? So those are interchangeable. So once you make your phosphonium ylide, this is your Wittig reagent. You could draw the structure either way. You want to recognize the structure either way when it's over the arrow in one form or the other. This is not something you just start with. It's odd looking molecule, right? You have to make it from something more conventional or simple, like our favorite starting material, the alkyl halide. So whatever R group you wanted here, you get that alkyl halide. Then you add step 1, PPH3, triphenylphosphine. Step 2, butyl lithium. Then you get your ylide. We'll do the mechanism in a minute. Then we get our ketone or aldehyde added to the Wittig reagent. So this section right here is where the actual reaction's happening, the Wittig reaction. So you're making the ylide, then you are reacting it. Okay, so let's show what happens. We get our ylid. Let's just color code this. I think I'll do green for all the carbons that were present in the ketone or aldehyde. And then I will do blue. I used blue already. Black for the carbon I have right here. So this was from my alkyl halide. All right, that whole section. So that black section here, stitched together with this green section here. Note that we can recognize that the R prime is that R prime. Carbon, carbon. Connected to an R or H, connected to an R or H. That makes a double bond with, oxygen's gone, by the way, the new carbon, which is on the ylid. That carbon that was on the ylid had an R and a C, an H attached, R and H. Okay, so that's how you construct your new alkene and figure out what goes where. All right, so let's go through that mechanism because it only makes sense if you kind of see some of this mechanism. So what is this Lewis structure of? Phenyl, phenyl, phenyl on a phosphorus. That's triphenylphosphine. So you'll often just see it written like this, PPH3, right? But it's written out just so you're comfortable also seeing it in its full glory. The lone pair on phosphorus attacks your alkyl halide that you start with. So you you're halfway there to your ylid. You have your positively charged phosphorus. This is butyl lithium. Specifically, you might even see it called N-buli for N-butyl, meaning there's not any branching as opposed to like P-butyl, isobutyl, right? So it's N-butyl lithium. So this is actually a very strong base because there's remember, lithium reagents have a delta plus and a delta minus, so they can act as a base as well as a nucleophile. So it actually acts as a base here, and it takes off. This proton is now acidic. So we take that H off. Why is it acidic? Let's see why it's beneficial to remove that H as opposed to another H in that molecule. So here's our ylid. It's our conjugate base. It's really just an acid-base reaction for that second step. All right, we made our ylid. So that second step where we took off the H, well, I knew I needed to make an ylid, so that means I knew that I had to have the carbanion next door to the phosphorus. However, because that phosphonium's there, it makes more sense to take off that H, simply because it allows me to have resonance. So I'll write that reason here. I chose the most acidic H, of course, thanks to resonance that is offered by the conjugate base. Well, what do I mean by that? Take a look. Here is my ylid in the form that is shown with two charges. That means there's a lone pair there. Here is the resonance structure we alluded to earlier. Oops, I forgot an extra P there. There we go. PH3. Okay, so either one of those forms will be shown. Actually, sometimes even more often, the one that doesn't have the ylid representation, the two charges. So just be aware that those. I like the ylid because it reminds us who the nucleophile really is. But a lot of books favor not showing the ylid and showing this form. So you'll want to kind of be comfortable going back and forth, or they might just interchange them. Let's do the mechanism, and you'll see what I mean by taking advantage of looking at the ylid so we know which one attacks where. I think it really helps in the mechanism. But if it's just over the arrow for predict the product, not so big of a deal. So let me show you what we mean by that. Okay, let's draw the full mechanism. How do we get to the actual alkene at the end? So let's do the ylid we just made. So if you don't remember, I'll redraw it here. That kind of isobutyl group. Now we could do this mechanism with either resonance structure. We can attack with the alkene pi bond or with a lone pair on carbon. Who will we attack? this carbon is the nucleophile. It's going to attack the electrophilic carbon, as usual, right? The carbonyl carbon, and that will open. So far, that's not surprising. Attack open. And because we're going to make, this big long arrow represents a new carbon-carbon bond we're about to make, and we're stitching together 2 carbon chains, I think it's a really good idea to number at this point, so we don't lose track. So carbon 1 is the one we're attacking from the nucleophile. And so this had 4 carbons in its chain. And let's call the destination carbon, carbon 5. And it has 3 carbons in its chain, so it's going to go up to here, 7. Here we go, 7. Okay. Now we're ready to put them together. All right, so I have an ethyl. I have an H. I'm actually going to start numbering that so you can see the logic that I have there. 7, 6, 5. That's from the left guy. 5 is now connected to 1. Carbon 1. 1 is still connected to PPH3 plus, and 1 is also still connected to that chain here, right? 5 had a carbonyl, and it's not a carbonyl anymore. It opened, attack open. So now it's an open carbonyl, which means an oxyanion. I'm specifically drawing them next to each other like this for a reason, because of what happens in the next step. And this intermediate has a name. This is called the beta-ene. So when you get to the beta-ene, you know you're on track to the next step, which is to form the oxyphosphatane intermediate. And to do that, it's one simple arrow. This oxygen is highly attracted to that phosphorus. It attacks. And so we make this 4-membered ring, briefly. All the rest is the same. I'm not going to draw all the H's. Oops. Okay. This is called the oxyphosphatane intermediate. So let me put this in quotes so we know. That's important to recognize. Oxyphosphatane. And when it's named, there's a reason, because it helps you kind of pinpoint where you are in the mechanism, and it's a neutral intermediate. So those are usually also named. So we clearly are not supposed to have a 4-membered ring. And in fact, our final product needs to be a carbon-carbon double bond, an alkene. And that means the oxygen's gone. So in other words, it's a byproduct. So we show that step here. Oxygen breaks off from carbon there. And as phosphorus accepts that double bond to oxygen, phosphorus breaks away from carbon there. And hence, voila, there's our alkene formation. So as a byproduct, so I can write byproducts coming off like this, a little curved arrow, or I don't really like it going toward the middle, so usually they kind of go off the outside. There we go. Something we didn't want to form, that wasn't the purpose. There's really no way around it though. In fact, they're annoying to form because you have to go purify it later and separate it. And I happen to know all too well because I did many Wittigs in my graduate degree, and that one is not fun for some reason. It was really sticking to a lot of my products, and I have lots of memories of finding that in my NMRs more often than I'd like. So it's there. It's just part of doing a Wittig. It's the byproduct that has to happen, because when you form that alkene, this comes off. But it's part of the territory. Got to purify it later. Okay, eventually did though, so there's happiness there. It was it felt extra good because I guess it was so hard. All right, so now look at what's going on here. I'm going to do this in yellow so I don't muddy it up too much, but this is all that's left of the carbon chain, and that's where the pi bond is. And I might add, I didn't draw them in this time, but there are still H's here. So when we form the pi bond, do I know if the H's are going to be on the same side or opposite sides? So in other words, am I going to have trans H's or cis H's, or more appropriately E and Z, right? So here's my R group, isopropyl in that case, and then where's the other one? Ethyl. Or are they going to be on the same side? Okay, so this would be Z, this would be E. So it turns out both form, but the major is, what might you guess? We like big groups away from each other, so yeah, it's E, major. But you could still get some of the Z as a minor product. Okay. All right, so this is a Wittig start to finish, including the mechanism. You have your aldehyde, you have your ylide, you take one carbon chain, take the other carbon chain, and connect them using an alkene. Can we look at them backward? What if we had the product? Could we draw the starting materials? That's a retro analysis. Just one step back retro. So, in other words, we're going to make our point of disconnection the very bond that is formed in a Wittig. Can you do that and say, what could I have formed one step back? Well, there's actually two possibilities. So I'll do them in red and I'll do one in green. Because there's a left and a right. I could let my left side be an ylide, my right side be a carbonyl, or I could let my right side be a carbonyl, my left side be the ylide. So let's try both. So since I still have my green ink on, I'm going to do the left side, the ylide. Plus, so that's what it would look like, chopping right down there. The ylide, if it was on the left, that carbon, the first carbon on the left, this one, would be where the ylide is. The first carbon on the right must be attached to a double bond O. Or we could have the reverse. That immediate carbon on the left is attached to a double bond O, and the carbon on the right, those two carbons, are part of the ylide. So, it says determine the best route. Well, right now, either one of these actually looks like they'd work, but know that we never start from the ylide, so we're going to go one more step back. Where did this come from? This came from this alkyl halide, right? Where did this one come from? Oops, this one came from this alkyl halide. How did we get here? We had to add 1 PPH3 to NBULI. So do that again, 1 PPH3. That's the steps you have to take to make your Wittig reagent, BULI. All right, so what happens when we do PPH3? Just draw a little mini mechanism here. Kick that off. It's an SN2. Okay, now we know something about which one would be better because we know what SN2 prefers. Primary versus secondary. So if someone said, make this molecule, pick the correct halves that are the most efficient, this would be the winner because SN2 prefers primary. So primary RX is better. Okay, that's the most efficient route. All right, so we want to be able to think forward and backwards with your Wittig reactions and do some more practice with that. Do one more practice problem. I'm going to try to show you how to do it kind of quickly and why we like the Wittig so much. Some students are kind of hesitant to use it because it looks weird at first, but you've really got to dive in and just start using it because it's a name reaction. That's a sign it's been given a lot of clout, and It really does show up a lot. Like I said, I used it in my graduate degree, which wasn't as long ago as the time it was invented. So it's in your textbook still for a reason. So why do we need the Wittig reaction? You might say, well, I can make alkenes other ways. So one thing you could say was, well, how about if I just take this ketone and I do a Grignard with it. If I do that, I have the methyl alcohol when I'm done. Okay, so methyl alcohol. And then I do an elimination. I'll have an alkene. So I can do 2 steps of very familiar reactions with very easy mechanisms, and then I won't feel so overwhelmed. But you will get what alkene? You're going to get Zaitsev's alkene. What is different about what we get with the Wittig alkene? Let's take this carbonyl, and I'm going to show you the quick and dirty way to do it. You'll still have to know the mechanism, but if you're trying to press for time and trying to just get the reaction out because you're doing a synthesis or just predicting your product as quickly as possible, this is kind of the way to do it. Know that your undesired product, that contaminant that plagued a lot of grad students' existence as they had to purify it, triphenylphosphine oxide, those go off together. That's your product, your byproduct, right? What's left? Why, your alkene, of course. These pieces. So you simply attach those together. And if you have an E or Z option, then you go for E is major, but we don't have that option here. Well, that equals, that's the same as drawing this, right? So if you're looking up your answers or it was multiple choice, it would look like that. So this would be like the Hofmann looking version. I wouldn't call it Hofmann because we don't use that selectivity to get the exo, but that means outside the ring. So this is major, would be Zaitsev. We have very little, possibly, but remember there's always a little. This is your Hofmann product with an elimination. So here's your major here, and this is your only product. So it depends on what alkene you want. And you might say, well, I could do a bunch of things to make sure I get Hofmann, but then you're doing a lot more steps. So Wittig is very powerful because you could start with this ketone and end with an alkene. This is already 2 steps, this is 1. So pretty exciting stuff. Okay, so get comfortable with Wittig. You see a synthesis that has an alkene as kind of a major transformation step, and the number of carbons has grown. It's a sign that Wittig is at play. Okay, so we're going to talk about another name reaction, the Baeyer-Villiger reaction. Villiger, first of all, was eventually a student of Bayer. Bayer, also known as like Bayer Pharmaceuticals, like Bayer aspirin, is very famous, one of the most famous chemists of all time. He is credited not just with this reaction, but you may have heard of something even more widely used, barbiturates, those prescription drugs that are also addictive. Apparently, he named him after his girlfriend, Barbara. So that's the etymology of barbiturates. He was thought to be kind of an interesting fellow historically, and actually rather nice. He was very, he didn't let his ego get the best of him, even with all his successes. He was very willing to share the merits that he earned with those that rightfully deserved it and worked hard with him. So probably why this reaction has 2 names. He wasn't insistent on claiming it all to himself. So that's pretty admirable. So I thought that was worth bringing up because sometimes that's hard to come by. He was also, in the history I read, that he was known to tip his green hat when he encountered a compound he thought was really interesting or new. So it's kind of a cute little background story for this chemist behind this reaction. So what is the Baeyer-Villiger reaction? When you take a peroxy acid, remember that is something like MCPBA or any other R group, doesn't have to be metachloro peroxybenzoic acid, excuse me. It could be other R groups as well. So e.g. MCPBA, Our CO3H, if we draw that out, it looks like a carboxylic acid with an extra O in there. And so that's like a peroxide, that's hence the peroxy acid. Ketones and aldehydes, when they are in the presence of a peroxy acid, because those are oxidizing agents, they will be oxidized to ketone to an ester, the aldehyde to a carboxylic acid, as shown below. Ketone becomes an ester. See that the new piece is the O that's now there. So one of the O's from here ends up in there. And this also likewise gives an O from the peroxy acid, inserts in there. So we get the carboxylic acid. All right, so let's do an example. Methyl ethyl ketone. Got to draw that out first. Plus peracetic acid. Acetic acid is vinegar, so this is acetic acid. Peracetic acid means we have an extra O. So that nomenclature, you want to be familiar with that. That's back from Chem 60, like peroxide means you have the extra O, right? So peracetic acid. We will get what? Well, we learned we turn ketones into esters. However, we have an asymmetric ketone. So I don't want to erase it. We have an asymmetric ketone. So is the oxygen going to go on that side or that side? Let's draw our proposed products here. Which one? It turns out it actually matters. It's regioselective. So when you have a choice of where to put the oxygen, you're going to consider the following. The migratory aptitude of the groups attached directly to that carbonyl. So what does that mean? That means that you're going to see soon in the mechanism that what happens is one of these two R groups temporarily detaches and reattaches as in a migration. So it's hence migratory aptitude. So it's like a 1-2 shift, in other words. And so when you do a 1-2 shift, you have something that could even possibly temporarily be a cation while it reattaches. And so in order for that to happen, the more stable the carbocation, the better the migratory aptitude. So H's make wonderful cations. So H is the easiest one. We do hydride shifts all the time, so that's not a surprise. And tertiary is a better carbocation than secondary, so when it comes to carbon chains, which is better than, well, and you know we might even see a phenyl in there. I'll put that there, which is better than primary, which is always better than methyl. Okay, so that's the migratory aptitude. If we follow that rule, that means that we would rather insert and move around something that was, let's see if we circle both sides. If we take that off, we have a primary group. If we take this one off, we have a secondary carbon that we worked with. So according to the ranking below, secondary is better than primary, which means we do not form this and we only form that. The mechanism shows this migration, so let's work on that. It's a fun mechanism, as you can probably imagine. So let's draw out our ketone with our peroxy acid in its full structure. Okay, now we are going to draw the product and show how we get to that mechanism, or show how we arrive there. Okay, so we need one of those oxygens to end up here. So one place to start is to attack the carbonyl, which is why it's in this chapter. That's the mechanism we've been doing all this time. Attack our carbonyl and open. O minus. And then everything that's attached to that O comes along with it. All right, now Think about my end goal. I only want an O from this whole thing. I don't want all of this other stuff. I want to keep this O, right? Because it stays there. So I'm going to try to work on letting this all sort of move around, and I'm going to do a proton transfer. And I'm going to choose to take it off of here because I need to keep the O. I don't want it to leave. And it's a good leaving group right now. So I'm going to take the H off, and I'm going to transfer that proton to somewhere else that would allow me to work on getting this off. And what I'm going to do is put it on the carbonyl because that'll activate the carbonyl. H plus transfer. Now I'm going to give myself a little more room because we have it. So sorry about that. I'm going to move this way. H plus transfer. There we go. Now it's nice and neutral there. Oops, forgot my O right there. Activate my carbonyl, and voila. Okay, now I hope you're ready for the most exciting step that reveals it all. Lots of arrows here. Close the pi bond, migrate, we're doing 1-2 shift. So here's our spot number 1, lasso that R group. It's the one with the best migratory aptitude. It's going to shift to the second atom over, which happens to be an oxygen in this case. So that's the first time we did that. As that oxygen accepts those electrons, it must release. And by the way, the OO bond is weak. That's why peroxide decomposes so easily to water. It's a weak bond. Heteroatom bonds in general are weak. So this is easy to break. So that's not a surprise that that would happen. And as it breaks, it gives all of its electrons to be shared between the oxygen and the carbon, which allows us this carbonyl carbon to only accept them in the pi bond if it opens this up, thus relieving that oxygen of its positive formal charge. All right, that's a doozy. Now, I'm going to write over the arrow to remind us the main thrust of this step was the alkyl migration. Okay, now what story did those arrows tell? Close a pi bond, methyl still attached to that newly reformed carbonyl. That's what I have so far. Ethyl's gone from that carbonyl. This is gone. O is still attached. Let's draw that in. Ethyl is no longer attached to the carbonyl, but it is attached to the other side of the O. Let's draw the rest. The oxygen has the methyl on it alone, so that's done. That matches this. Okay, so we've really proven our point here. But let's draw the byproduct. So this set of electrons that broke it off made a pi bond here to make it a carbonyl. Then our carbonyl that was activated opened up and became an OH. On the other side of that carbon, there's a methyl. So that's our byproduct, and that is, lo and behold, acetic acid. So we get a carboxylic acid, and the reason I'm taking the time to point that out is to also let us note that this is a true oxidation. Look at what happened here. This peroxy acid is our oxidizing agent. I'll just draw that in brackets. Oxidizing agent. And our oxidizing agent got reduced. It lost the bond to oxygen. So it kind of proves what kind of reaction this was. Okay. So you want to be able to not just do this mechanism, but also go do some problems and see how you can solve them on your own. I'll do these last two with you though. So migratory aptitude. Always what you consider. You know you have a Baeyer-Villiger because we have peroxy acid and an aldehyde or ketone. Now, H versus secondary carbon, H wins. We get a carboxylic acid. Leave that other side alone. Tertiary versus secondary, once it's detached, in other words, the more substituted wins. So we get this ester. This side stays the same, and the ring grows by one more carbon size. So I left that one out. Very ugly 7-membered ring there. I apologize. It's kind of disgraceful. I'm gonna have to give that a little bit more. All right, so the way I like to draw a 7-membered ring, just because they are hard to draw, is draw it kind of like I would have had a stop sign, maybe, until we get to the point. So you can start the bottom of a stop sign. And I'm only doing this because I know I have a 7-membered ring. And so then we continue our octagon. And instead of doing the last one aside, make it a point. And I know that last atom is an oxygen. That's reasonably better, right? It's not beautiful, but it's more respectable than before. Okay, so methyl here and that one there. Much better. Okay, so go try some more, have fun, and we'll see you soon.